All right, so welcome everyone again to our Spring 2023 seminar series. This afternoon, we are privileged in two ways. One is our speaker, Professor Blaney, and second is our co-host, Gabrielle Francisco. So Gabrielle, I'm going to go ahead and introduce her. I think all of us online here, or at least on the Andrew side, knows Gabrielle. She's a senior studying biochemistry and sociology. She's passionate about interior design, food, likes to play sports as well as paint when she has the time. I've never seen any of your paintings. We're gonna have
I can show you a couple.
We're gonna have to change that, yes. She works as a pharmacy technician at Walgreens Pharmacy. She also writes for the ideas section of our student paper, Student Movement. She loves history, cultures, plans to travel. If you heard the conversation she was having with our speaker today, and she enjoys learning different languages. Her ultimate goal is to become an attorney, possibly a judge. She's still figuring things out. So it's a privilege again to have you. And so could you go ahead and introduce our speaker?
Yes, thank you, Dr. Murray. Today I have the privilege of being able to introduce Dr. Lee Blaney. He is a professor in the Department of Chemical, Biochemical, and Environmental Engineering at the University of Maryland, Baltimore County. He holds BS and MS degrees in environmental engineering from Lehigh University and a PhD in civil engineering from the University of Texas at Austin. His research program focuses on, one, the occurrence and fate of contaminants of emerging concern in natural and engineered systems, and two, recovery of nutrients and other resources from waste streams. His research program has been funded by the NSF, USDA, EPA, SERDP, and USGS, among others. He is the recipient of the ES&T James J Early Career Award, the NSF Career Award, and the AEESP Award for Outstanding Teaching in Environmental Engineering and Science. He serves on the board of directors of the AEESP and the executive committee of the ACS Division of Environmental Chemistry. And without further ado, Dr. Lee Blaney.
Yeah, thank you very much, Gabriella and Dr. Murray. So just give me 1 second here to get my screen sharing.
Okay.
And I'm going to open up the chat on the side here. That way, if people have questions in the middle, you can interrupt, or if you want to save to the end, that's also fine.
Okay. So you could do full screen.
Oh, actually, let me stop sharing 1 second because I think I forgot to click that button that I was telling Dr. Murray about earlier.
Okay.
For sharing the sound. So I have a video. So, okay. All right. So, well, thanks again for the nice intro. And today I'm excited to tell you about our work looking at recovering nutrients from poultry litter, animal manure, using a technology that we developed called the Phosphorus Extraction and Recovery System, or PAIRS. I will give you a quick warning here. I'm recovering from COVID. And so if I suddenly get quiet, don't worry, I probably just muted myself so I can cough without kind of blasting that into your ears, and I'll be back as soon as I can. But yeah, thanks again to Dr. Murray for the invitation. I've been looking forward to this talk and having a chance to share our work with you. I need to start by acknowledging our team at UMBC. I'm very lucky. I have a great team of undergraduate researchers, graduate researchers, and postdocs in the lab. They're all shown here. You can see we have a very diverse group. They come from all around the world, and that really kind of gives us the best opportunity to take advantage of different perspectives, different life experiences, and bring all of that together to make sure that we're doing, our best research and putting forward the best technologies. It's really my privilege, to work with this group. They do all the hard work. I just get the kind of privilege. I get to walk around and travel around and share our projects with everyone, including all of you here at Andrews University. But all the credit goes to them. And as Gabrielle mentioned, our group, we kind of have two primary areas. So the second one here on recovering vital resources like nutrients from municipal and agricultural waste streams, that's going to be really the topic of my talk here today. So I'm not going to mention that one on the slide, but I'll just give you a quick introduction to our work in the first area, which deals with the occurrence, fate, transport, and toxicity of contaminants of emerging concern. These are things like pharmaceuticals, personal care products, hormones, kind of like consumer chemicals that you wouldn't necessarily think of as pollutants, but we do. We think about them in the natural environment, such as kind of, rivers and streams, as well as the engineered environment, basically drinking water treatment plants, wastewater treatment plants, because they can have some unintended consequences. Does anyone have a sense of an unintended consequence of pharmaceuticals, personal care products, or hormones in the environment? I got the chat open, so you can just throw it in the chat if you want. Well, I'll let you think about it. But I'll tell you one example that we focus on a lot is antibiotics. So when antibiotics get into the environment, which they eventually do, they can cause the development and spread of antimicrobial resistance. This is a huge public health concern. There's estimates that by 2050, antimicrobial resistance will be the #1 cause of death. And it currently costs like over $30 billion in the US dealing with this issue. And so antibiotics in the environment is just one aspect of that picture. But it's, again, one of these examples of, these chemicals weren't really designed to go out into the environment, from a public health perspective. And if they have these unintended consequences, it can kind of cause big issues. So if you're more interested in that area, I'm not going to talk about it too much today. I'm going to revisit it pretty quickly at the end of the talk. But you're always welcome to, ask questions about it or reach out to me separately. Okay, but for today, I'm going to, I see Gabrielle has a thing. Yeah, so harms to the water we drink, and the animals. I'll give you one more example since you mentioned animals. The figure here shows oysters, but we had a previous project out in Hawaii. So 2 of my PhD students got to go to Hawaii because there's some concern that the chemicals that are used in sunscreens, such as this one that's shown here on the left-hand side, it's called oxybenzone, are actually toxic to corals. And so they went out to Hawaii, collected a bunch of water, sediment, and coral tissue samples. And then we analyzed for the presence of these sunscreen chemicals, to inform that issue. And actually last year, I presented to the national academies on some of that work to inform potential regulations on sunscreen chemicals moving forward into the future. Okay, but for today, like I said, I'm going to mostly focus on the topic of nutrients. I kind of have this talk split into 2 main parts. So the first is going to be like a lot of our motivations for thinking about recovering nutrients from waste streams. And then the second part, I'm going to tell you more about our pairs technology. Okay, and again, I have the chat open, so if you want to ask a question, anytime in the middle, please feel free. That doesn't bother me. So why nutrients? First, they're essential. We need nutrients to make fertilizers to grow food. Ever since the Green Revolution, which was basically introduction of fertilizers to improve agricultural efficiencies, we need to use more and more fertilizer every year. Our global population is growing exponentially, so we also need to produce more food every year. We need nutrients to do that. The 2 main nutrients of most concern for us are nitrogen, which we generally kind of convert into ammonia from N2 gas in the atmosphere using the Haber-Bosch process. and phosphorus, which we generally mine as phosphate rock, and it's a finite resource. So phosphate rock, you can kind of think of it like oil. You know, there's a limited supply of it. Once we kind of run out of those rich reserves, we're going to need some new solutions. If we can recover phosphorus from waste streams, that will help us sustain our current reserves and also be, a sustainable option in the future to try to close the phosphorus cycle. So we kind of use it and then recycle it and use it and recycle it. That would be ideal. Okay, especially because our phosphorus reserves are expected to reach their peak production sometime in the next few decades. Okay, and again, the world's population is growing. We're using more fertilizer per capita every year. So we really need some alternative solutions for sourcing phosphorus. And I think probably many of you have kind of heard some of the issues with nutrient pollution in the past. So if we discharge a lot of nutrients into water, it can cause algal growth. This is actually an experiment that was done in a real lake. So they split this lake into two sections and they added nutrients on the bottom side. They didn't add any phosphorus on the top side. You can see this is so much greener. That's because of the algal growth. And then one of the problems with algae growth in water bodies is they grow up very fast and then they die. And when they die, they consume the dissolved oxygen in the water, as the algal cells get broken down. And then this causes what we call hypoxic zones or eutrophication to happen. Basically, there's no dissolved oxygen. And so the fish and the crabs and the oysters and all the stuff that wants to live in the water can't live there. Okay. This causes big consequences for tourism, for fisheries, for biodiversity. And it's one of the kind of major causes of pollution or sources of pollution in our country. Okay. It's definitely a regional issue. We know that very well in the Chesapeake Bay area. I'll show you some other places in the country that know that very well shortly. Definitely a national issue, and it's becoming increasingly a global issue. Okay, so I'll start kind of in the US. A lot of our concern with nutrients comes from wastewater. So that could be human wastewater, when you flush your toilet, it goes to a wastewater treatment plant. One of the goals of those wastewater treatment plants, depending on where you live, is to try to remove nutrients. Another big source is agriculture. So both crop agriculture, we apply fertilizers. Some of those fertilizers run off and get into rivers and streams. But also when we produce animals, those animals produce a lot of waste, and that waste contains a lot of nutrients in it. One of the issues with animal agriculture over the last 40 years, I hope you can see here, this is the pounds of meat, from these 5 major animals available per capita. So if you kind of sum all of these up from 1910 versus 2010, you can see that the total number is much higher in 2010, which means we're producing more meat per person. It also means we're producing more animal waste per person. And you can also imagine that our country's population has increased quite a bit, from the early 1900s till now. The biggest increase has definitely been in chicken. Okay, this is one of the reasons why we've focused our nutrient recovery technologies on hatchery operations so far. I'll tell you some other reasons as we move forward here. Okay, so I already kind of gave this part away, but we're producing more animals, and with that, we're also producing much more animal manure, which is again very rich in nutrients. Now, some of you, if you're kind of like myself, I'm from Philadelphia, I'm from a city, so I don't really know what a farm looked like when I was growing up. I had kind of the maybe conventional picture of a farm, animals in the field, something like this. But increasingly, especially in the US, we have what's called concentrated animal feeding operations, or CAFOs. And these are, much more engineered, kind of organized factory-like farms. They produce a lot of animals in a very small space, which means, again, they're producing a lot of manure in a very small space. It's not spread out over fields and pastures and things like this. Okay. Now, what animal is being produced kind of depends a little bit on where you live. If you look at the map here, the blue color, the darker blue means that there's basically more mass of phosphorus in the animal manure per square meter of space in that state. Okay, so it's kind of normalized to the footprint of each state. I hope you can see that the three darkest states here are Maryland, Delaware, and North Carolina. Maryland and Delaware have very concentrated, very dense poultry operations, and North Carolina has very dense swine operations, pig operations, basically. If you compare to the national averages here, you know, the amount of nutrients that are generated, again, kind of normalized to farm area, is way higher for Delaware, Maryland, and North Carolina. Okay, especially for phosphorus, which is one of the things, you know, that we're quite interested in. Now, when we think of pollutants, you know, from our kind of environmental engineering framework, which is the base for our group, we oftentimes think about point sources. So a point source would be like a wastewater treatment plant. There's basically one pipe that comes out of it, and we can do some additional treatment. We can add processes upstream of that pipe. Okay, and if we do that, we're able to limit, you know, the nutrients that are present in the effluent. Another type of pollution is called non-point sources. That would be like if we put fertilizers onto crop fields, or if we have animal manure, you know, that's potentially being mobilized into surface waters like rivers and streams. There's no pipe. And so it's very hard for us to try to like collect that water that's running off of a field, or collect that water that's running through some manure, you know, lagoons or piles, and try to collect it and treat it. Okay. And so from a Chesapeake Bay perspective, which is kind of where I'm coming from a lot of this talk, it's pretty easy, you know, if we want to be able to treat nutrients in wastewater, but it's much more difficult to treat nutrients in agricultural operations. And again, this is one of the drivers for us to develop the PAIRS technology to find maybe an innovative way to do this. Just to emphasize, you know, the importance. So I talked a little bit about, you know, how nutrient pollution causes eutrophication, the formation of dead zones. So this is the Chesapeake Bay here. If you don't know, it's the largest estuary in the United States. So it's very important from that perspective, you know, also very important for fisheries, recreational activities, tourism, you know, and plenty more. Every summer we have a dead zone that forms in the Chesapeake Bay. So that's this red zone right here. Wherever the dissolved oxygen falls below 2 milligrams per liter, that basically, there's not enough oxygen in the water to support aquatic organisms. So this is terrible for us, you know, if we're trying to produce oysters or, you know, some of the fish species that are kind of specialties around here. So we want to try to limit the formation of that dead zone. And we need to think about both point sources like wastewater treatment plants and agriculture as the sources of the nutrients that are causing that dead zone. Okay, but as I said, this is also important around the world. So all of these red dots that you see here, these are dead zones. You can see that the east coast of the US and the Gulf Coast of the US are very rich in dead zones. Okay, we also have some on the Pacific side. Europe, there's a lot more smaller dead zones, except up here in the Baltic Sea, you know, very kind of heavy impacts in this area. Out in Asia, a lot of dead zones around Japan. Okay, the number of dead zones that form continues to increase decade by decade. You can see it's kind of exponential growth here in the yellow bars. Okay, Green Revolution was like 1960s, 1970s, and so you can see things have really taken off since then. Okay, so one other aspect that's really important here is even though the impacts of nutrient pollution are global in scale, where we get our phosphorus from is much more geospatially limited. So I'm going to ask y'all a question again. Does anyone know where most of the world's phosphorus comes from?
Is it Russia?
It's not Russia,
Oh, okay.
but thank you for the guess. Students, you can use the chat too. Don't be shy.
I looked it up. It says China and Morocco.
All right, Gabriella, very resourceful. Morocco is really the big one.
Okay.
So almost, from this report in 2011, almost 3/4 of the world's phosphorus reserves are in Morocco.
Hmm.
And at least, when they did this study, they projected out and said, okay, what's the remaining reserves going to look like in 2020? So you can see, the kind of amount went down a little bit here based on the estimated use in that time period. But then actually Morocco's share went up, which means the other countries are kind of using their reserves much more quickly.
Hmm.
This is really important because, I kind of tell people, hey, Morocco could wake up tomorrow and say, okay, phosphorus costs 100 times what it cost yesterday. This is a big economic liability. And it's really important because, again, we need phosphorus to grow food. So the world's population is growing up. Countries need to buy fertilizer to be able to support their populations. And if one country has control of most of the reserves, that really kind of adds, not just economic liabilities, but also political liabilities, and all kinds of issues on top of the water security and food security issues that are a little bit more inherent to agriculture. This is another reason why, if we can take advantage of recovering phosphorus from our waste streams, we can reduce that reliance on one country and actually extend, the lifetime and the sustainability and resilience of the Moroccan reserves. Actually, it's really interesting. I don't have a photo here, but if any of y'all are interested, you can actually, if you go into Google Maps and look pretty close to the border between Morocco and Western Sahara, which is kind of a territory of Morocco, you might be able to see this kind of like thin white line. That's like actually a conveyor belt that runs from the big phosphorus mines in Morocco out to the coast, where they ship everything out. And so you can see it from the satellite without zooming too far in. It's actually pretty interesting. Okay, so how can we improve the situation moving forward, and who needs to be involved? So one thing that we really need to think about, between now and, maybe 2100, in the next, let's say 50 years, is how can we start to reduce our phosphorus demand? If we don't do that, you can see this graphic is saying, okay, it's going to keep increasing, and we're very quickly going to drain our reserves, and run into some of these potential political and economic issues. There's a few things that we can do, to change that course. Many of these are more focused on using the phosphorus that we have more efficiently. So there's opportunities for us to change some agricultural processes, change some food supply processes, change diets. So I think we're, at least in this country, probably moving, a little bit away from animal meat based diets now. There's more alternatives available, and I think they're gaining more traction. These are opportunities for us to reduce that phosphorus demand, but there's also opportunities to reuse phosphorus, recover it from waste, and basically recycle it as new fertilizers. This is where we're really coming in. So today I'm going to focus on manure, specifically from poultry operations. But I will mention, we also focus on phosphorus recovery from municipal wastewater, so kind of human wastewater. We've also done a couple of projects. We're a little bit in the starting point here of saying, hey, can we actually collect urine separately, recover the nutrients directly from the urine, and then send it down the sewer, to the wastewater treatment plant? There's actually a lot of benefits in that because it's more concentrated if we kind of recover it from urine, and that actually makes things much more efficient. It also allows us to save a lot of energy and cost during wastewater treatment because the nutrients get more diluted there and it's actually harder to treat. So we have a lot of projects going on in these kind of areas, but today, again, we'll focus on manure. One reason why we are really looking at animal manure most heavily in our lab is just the scale of it. Okay, so if you think about it, every year in the US, we produce about 7 million tons of dry waste solids. It's basically wastewater sludge. That seems like a lot, but you can see it's almost 2 orders of magnitude lower than what gets produced by animal operations. And so really this is where we have the most potential to have the biggest impact, you know, on not only recovering nutrients as valuable fertilizers, but also reducing nutrient pollution into the environment. This is where we can make the biggest impact. Okay, but let me tell you one reason why I'm really kind of glad to live in the Chesapeake Bay watershed. So here's Baltimore City right here. Here's UMBC, my university. Here's Washington, D.C., if y'all have visited. This is Chesapeake Bay kind of running up the center here. Okay, so it extends right here. The satellite image changes a little bit. Okay, but it extends up through here. Now, the western side of the bay is very urban, kind of dense urban corridor, DC, Baltimore, and then up to Philly. All of these red dots are wastewater treatment plants. Okay? Many of these are quite large, 100 million gallons per day, 200 million gallons per day. Washington, D.C.'s treatment plant is over 1 billion gallons of wastewater every day.
Wow.
So this is a big source of nutrients from the western side of the bay. On the eastern side of the bay, all of these blue dots are poultry operations. And so it's kind of a very interesting test bed. This is like maybe my reactor. I say, oh, the nutrients coming from wastewater, or are they coming from agriculture? Really, we don't care about that. We just say, well, can we recover both of them, turn them into fertilizers, send those fertilizers somewhere else, sell them somewhere else if they need them, because our soils, our waters, are already so rich in nutrients here in the Chesapeake Bay. We don't need it. So we want to export these, recovered nutrients and fertilizers somewhere that does need it. To maybe emphasize that case a little bit, here's a map of the Chesapeake Bay, but now the color on this map is showing the phosphorus that's kind of delivered to that area every year from agriculture or wastewater. Okay. One thing I'll mention is the darker the color here, that means more phosphorus is being delivered. In this case, I hope you can see the Delmarva Peninsula, which is, this eastern part of Maryland, the western part of Delaware, and then this little strip of Virginia here. This is like all completely dark red. That basically means that the soil in this area has almost no adsorption potential for phosphorus anymore. If we apply new phosphorus, whether it's as fertilizer or even if it's as poultry litter, that phosphorus is basically gonna just flush right off of there and get into water bodies because there's no potential for it to stick to the soil. It's just already saturated, already overloaded. The reason why that's the case is because every year on the Delmarva Peninsula, we produce 600 million birds. 600 million birds. That's 2 birds for every person in the country in this little tiny area of our country. 600 million birds. That means 1 to 2 million tons of poultry litter. Okay. There's a lot of phosphorus. There's a lot of nitrogen in that poultry litter. This is what's causing, this is the predominant cause of the dead zones, that form in the Chesapeake Bay. And actually, a few years ago, Maryland brought a new regulation that kind of said, okay, if you're a farmer and your soils, have a certain phosphorus content, you can no longer apply poultry litter to that soil. That soil is saturated. You can't apply new poultry litter because they're trying to reduce the amount of phosphorus getting into the bay. That law actually affects about 20% of farmers. So that right now they have to basically truck their poultry litter somewhere else. That's a huge cost. That's a lot of energy. That's leading to climate change potential, all kinds of issues. And it's like a headache for farmers to have to truck their stuff so far away, you know, sometimes 100 miles, 200 miles. So we thought, hey, if we can come in, take the poultry litter, extract the nutrients, convert them into a high quality fertilizer, whatever's left behind, you know, they can apply onto the soil. There's no phosphorus in it. It's still, you know, a good soil additive. It can help improve the health of the soil. And then again, the fertilizers that we recover, we can sell them somewhere else. So here's Lee Richardson, who's one of our partner farmers. And you know, he thinks this is really a win-win because the farmer gets something from their waste. You know, they look at their waste as a valuable resource. They don't want to just get rid of it, truck it away. And at the same time, you know, maybe this is a more sustainable way to do business, you know, for them into the future and, you know, pass their businesses off to, you know, their children and things like this. So we went out and, you know, kind of when we were getting started, we went out to a bunch of different farms, collected their chicken poop, brought it back into the lab, digested it, you know, and measured for the chemical composition. Here's just a snapshot of some of the species, you know, that we're most interested in from 4 different farms. So you can see we do have a bunch of nitrogen. It's mostly as ammonia or ammonium and not nitrate. This is a good thing for us. Ammonia is the more valuable form of nitrogen in fertilizers. And so this is what we want to recover. There's a lot of phosphate, of course, potassium, another important nutrient. We have some calcium and some magnesium. And you can see that the composition is pretty similar across these 4 farms. That actually makes a lot of sense. You know, there's actually not a lot of poultry companies at the top. And so you can imagine that their processes, their feeds, you know, all this stuff is pretty systematic at this point. And we didn't pick up big differences. That's also good news for us because it kind of tells us that our, you know, chemistry for the pairs reactor, you know, will be kind of consistent, you know, from farm to farm or poultry litter to poultry litter. Now, we took all of the chemical composition data that we collected, and maybe this looks familiar to some of you, log C pH diagram. So we took all these chemical compositions and we use a free tool called Visual Mintech. You can Google this one, you know, and play around with it if you haven't before. But you basically can enter a recipe and then it'll tell you, okay, these are all the chemicals that are present in water. So, you know, we have phosphate, 3- ion, but then we also have like calcium phosphate complexes, magnesium phosphate complexes, you know, the protonated forms of phosphate and so on. We can also plot in the dark black curve here. This is the total dissolved phosphorus. So when that curve goes down, that means some solid is precipitating. So one thing that we thought when looking at this log C pH diagram is, hey, if we have some poultry litter and we put it in water and we bring the pH down, we can release all of the phosphorus into the water. And then if we bring the pH back up, we can actually precipitate some of that phosphorus, hopefully as a high value fertilizer product, which for us, what we are trying to produce is struvite. So struvite is magnesium ammonium phosphate. This is a great fertilizer for a number of reasons. One, it's slow release, so it doesn't dissolve immediately. This is really great, you know, from a fertilizer perspective, because conventional fertilizers, they dissolve pretty much right away. You know, they're mostly like ammonium phosphates. So you can kind of just consider them like table salt. If you put them in water, they dissolve. And then you can imagine that those nutrients run off pretty easily. Struvite dissolves more slowly. And so you don't get like a big flux of nutrients after a rain event or after an irrigation event. This kind of helps keep the nutrients releasing slowly, getting into the plants and facilitating plant growth. And the nitrogen and phosphorus contents are balanced. That also helps to reduce the nutrient runoff. We do have some potential to also form potassium struvite, which is basically the same, except we substitute the ammonium with the potassium. We actually like to do that in our lab. If we can produce both struvite and potassium struvite, now we can mix them together and customize nitrogen, phosphorus, and potassium levels. And this is what farmers do for different crops. So different crops have different NPK ratios, nitrogen, phosphorus, potassium. And so if we're able to produce both of these, that's really great for us. One that we don't want to produce is called hydroxyapatite. So this is a calcium phosphate. All of you are familiar with this compound. Does anyone know why?
Isn't it part of our teeth?
Yes, you got it. So hydroxyapatite is the mineral that your teeth are made of, your bones. This is great if we're thinking about nutrient removal, but hydroxyapatite is basically insoluble. And so if we want to think about reusing, the recovered particles, it's not going to be that great for us because basically the phosphorus isn't going to release from the hydroxyapatite fast enough to get into the plants. So not very effective, from a fertilizer perspective. Okay, so now I've set you up for our pairs technology, and I'm going to give you a teaser first, and then we'll kind of step through step by step how the technology works. So let me play this video for you, and hopefully you'll be able to hear it.
Visit environmental engineer Lee Blaney's lab, and you'll likely catch a faint whiff of, well, a barnyard. It's understandable. The contents of this bucket may look like dirt, but it's actually poultry litter.
Poultry litter is a mixture of poultry manure, just chicken poop, extra feed that may not have been eaten by the birds. It could also be feathers. It could also be some of the soil on the floor of the poultry houses.
With support from the National Science Foundation, Blaney and a team at the University of Maryland, Baltimore County are developing a new technology aimed at treating poultry litter and recovering nutrients from the waste.
Poultry litter is actually, a great resource. There's a lot of phosphorus in it, there's a lot of nitrogen in it, and there's a lot of potassium. Now, those are kind of the three big fertilizers, so we usually call them NPK, nitrogen, phosphorus, potassium, and that's what plants need to grow.
In fact, many farmers use poultry litter from their chicken houses to fertilize crops. And that's where the problem starts, with agricultural runoff. Too many nutrients in the water feed algal blooms, which suck up oxygen. That, in turn, causes dead zones.
If you don't see it every day, if you're not a fisherman in the Chesapeake Bay or the Gulf of Mexico, you may not understand the scale of the issue. But if we take the Gulf of Mexico, for instance, last year the dead zone was the size of New Jersey.
So if it doesn't go onto the fields, what's a farmer to do with all that litter?
Poultry litter is a waste stream that currently we're kind of just throwing a lot of great nutrients and other resources away.
In Blaney's view, the solution is recycling. Extract the nutrients and then sell them for profit.
And so what we're trying to do here is really a win because we're protecting the environment and we're also generating a potentially new revenue stream for farmers.
To do it, they make a poultry litter slurry and pump it through these tanks. They add acid and carbon dioxide, which pull the nutrients into the water. They separate out the leftover runny solid, which look like, well, you know.
Then we take that water, we bubble air through it, and we add some base and we bump the pH back up. When we get to around pH 9, we're actually able to precipitate a molecule called struvite.
Struvite is a valuable slow-release fertilizer that farmers could then sell. And those leftover solids, the nutrients, are mostly gone. But the solids are still rich in carbon. Farmers can spread it on their fields to help soil hold more nutrients and water.
We really need to have a holistic approach to considering these systems, and especially our waste streams. And so if we're helping farmers generate profit, stay in business, keep producing the products that we use every day while protecting our environment, it really is a win-win for all of us.
Engineering new ways to recycle waste, creating new revenue streams for farmers, and protecting waterways. The Science
All right.
Nation, I'm Miles O'Brien.
So let me tell you a little bit more now. So here's kind of a schematic that we like to use to describe pairs. So basically we take our poultry litter, we throw it into water and mix it up. and then we start bubbling CO2 gas in. One of the things that we are kind of very interested in is ways that we can connect this with other environmental issues. So if we have waste CO2 gas, coming from an industry, we can kind of divert that, bubble that through here, and actually use that to benefit this process. It makes things more carbon neutral and can potentially be, maybe a minor carbon dioxide sink, for the world. As we do this, we also will add a little bit of acid that helps to pull the phosphate and other nutrients out of the poultry litter solids. Once we have the phosphate in the water, what we'll do is a solid liquid separation. And so we do that in the lab kind of, with a couple of different engineering technologies. The phosphate or nutrient enriched liquid will move forward in the process. These solids, again, they are low nutrient, and so they can be applied on the fields with no problems. And then we bubble some air through to try and knock that CO2 back out, add some base to bring the pH up to around 9. That allows us to precipitate struvite. And then the water that's left, we actually recycle it and use it for the next batch. Okay, so there's a lot of sustainability here. We're taking one waste stream, the poultry litter, a second waste stream, the CO2, using this to produce a valuable product. And then the third waste stream, the used water, that goes back around and gets reused. So we think this is, really a technical or technologically feasible option for farmers, as well as a sustainable option. So if we look at the phosphate extraction step, here's the fraction of phosphorus that was extracted as a function of pH. When we were generating this, we weren't sure exactly what pH set point we wanted to work at. So we had to do some tests, in this case, with 3 different poultry litters. You can see that we built some models here. I'm not going to get into that today, but I just want to emphasize we identified pH 4 to 5 kind of as our target. You see there's like a little bit of a plateau here. We could extract more, but we have to bring the pH down pretty low. That adds a lot of cost for us in terms of the acid costs as well as the base costs later on. And so this pH 4 to 5 is really the right set point for us. We looked at different things, if we change the slurry strength, so how much grams of poultry litter per liter of water we add, you can see there's some impacts on the phosphorus extraction. So as the slurry strength goes up, the phosphorus extraction goes down. That makes a lot of sense if you think about it. There's a lot more solids in there, and so there's more kind of binding potential, absorption of phosphorus onto those solids. That may be kind of more of a solid liquid equilibrium issue rather than anything else. Okay, but even here at 80 grams per liter, we were able to get maybe over 70% extraction. We felt pretty good about that. Now on the flip side, after we extract the nutrients, separate out the poultry litter solids, then we add the base and precipitate, the phosphorus that was in the water, we actually see kind of the opposite effect. So low slurries, we actually have very low precipitation efficiency for phosphorus. And more concentrated slurries, we have a much greater precipitation efficiency. This makes sense if you think about it. Over here, because there's less poultry litter, the amount of phosphorus that we're extracting is much less. That makes it a little bit more difficult to precipitate, more of it. Whereas over here, we're extracting a lot more phosphorus mass, and that makes it easier to precipitate on the on the back end, just due to the chemical equilibrium kind of conditions. Okay, so also as we precipitate our phosphorus, we weren't sure exactly what set point that we wanted to operate at. So here's the phosphorus that was precipitated in percentage as a function of the solution pH. So again, we're kind of doing our extraction at pH 4 to 5. So there's no solids here. And then we start basically bumping the pH up. You can see if we go from pH 4.5 to 7, we precipitate about 50% of the phosphorus that was in this extract. If we go up to pH 8, now we're like 90%, pH 9, maybe we're closing on 95% here. So this was pretty good for us. Again, we can increase it a little bit more if we keep going, but that adds more cost. And so we want to be cognizant of that. One question that we did find ourselves asking here, though, is, okay, we're precipitating 95% of the phosphorus, but what are we precipitating it as? These SEM, scanning electron microscopy images, show two solids. So these kind of little, kind of like rectangular solids, those are struvite. So that's the mineral that we want to recover. And then these big pieces here, these are actually calcium phosphates. We don't want to recover those. So we thought a little bit, how can we play with the purity so that we can recover more struvite, as well as a high amount of the phosphorus. So we actually went back, to chemistry fundamentals and said, well, maybe we can add EDTA, which has affinity for complexing calcium over magnesium. And if we add just enough EDTA to complex the calcium, maybe we can increase the purity. So we did that. That's what's shown in the purple here. You can see that our recovery efficiency, or our precipitation efficiency for phosphorus, decreased. That kind of makes sense if you think, okay, there's a lot of phosphorus bound in this calcium phosphate. Now we're blocking that, and so the overall precipitation goes down. But our purity goes way up. You can see all of these are basically, pure struvite, very homogeneous type solids. So that was good news. We said, well, maybe if we supplement a little bit of magnesium on top, we can get the best of both worlds, bump our precipitation efficiencies back up around 90%, and still get very pure solids on the back end. And we're able to do that. So we probably have a little bit more optimization to do on this side, but the fact that we have tunable recovery and tunable purity is very, very promising for us. Here's just another look at kind of how the process works. This is a case study where we were trying to see how much phosphorus can we recover in a single 45-minute run. So we could probably recover more, if we spent all day doing it, gave a lot of reaction time, but we wanted to be cognizant of, hey, we got 1 to 2 million tons of poultry litter to get through. We need to be a little bit quick with it. So here you can kind of track in the blue line how the pH changes through this run. Okay, and then the numbers here correspond to the steps of the pairs process, which is just shown here again to remind you. So you can see, we kind of drop our poultry litter in water. Immediately we release some of the phosphorus, start bubbling our CO2, adding our acid, we release even more. Here we separate out, the waste solids. We don't need them anymore. We extracted the nutrients. And then we move the water forward. We precipitate the struvite. And then here's how the extraction and recovery efficiencies kind of change from process to process, or process stage to process stage. Here's what the reactor looks like. You saw that in the video. One thing that I'll say here is, even though all my degrees are engineering, a lot of what we do in the lab is kind of environmental chemistry. When we built this reactor, this is the first time I really felt like an engineer. And I'm so proud. Like this reactor was mostly put together by my undergraduate research assistants. So all of you are undergraduate researchers, or undergraduate students at least. You're capable of building things like this. It's really cool. We put the poultry litter in at the top in this center bin, push a button on this computer, everything's programmed, it runs, it does everything. There's no other manual intervention needed. You just put the poultry litter in and press the button and it goes.
Wow.
So it's really cool. It's just really fun to operate and see the water shift from reactor to reactor and see the solids dump out and all of this stuff. So the video gave you a bit of a sense of that. I'm very proud of the team that assembled this, especially because they did all the controls, all of the reactor assembly, all of this pretty much on their own. When we take the big reactor, we ran a number of kind of larger studies through that. And so here's just one example. I'm not going to get into all of the data here, but I'm just going to give you the bottom line. We were able to recover over 80% of the phosphate, about 20% of the total nitrogen, that is kind of corresponding to the ammonia content. Over 95% of the magnesium and about 5% of the potassium. There's a lot of potassium. And so in this case, really, we are a little bit limited by magnesium. You can see we recovered most of it. If there was more present, probably we would have been able to bump the phosphorus recovery up a little bit more, as well as the nitrogen and potassium. But we're still pretty happy with this. When we went into this, we thought, okay, if we can get greater than 60% phosphate recovery, we'll be happy. We got over 80%. And I don't have a photo here, but we have a slight re-engineering of our pairs reactor that we put together. And now we're actually getting closer to 90%. And so we're very happy with this. Okay, and then we take all of these nutrients that we extracted and produce our struvite here. I'm going to come back to this question of composition shortly. But I also wanted to tell you about the recycle. So I told you after we precipitate the struvite, we take the process effluent and we recycle it back around for the next batch. Here is some data that we did for basically 10 batches of poultry litter slurries. Okay, the blue is our phosphorus release efficiency, the red is our phosphorus precipitation efficiency, and then the green is the overall recovery. So here's our 80% benchmark. When we went to stage 2, it actually increases. Stage 3, it increases again. That kind of stays for a couple and then it starts decreasing. This actually makes a lot of sense if you think about it. When we precipitate the struvite, we leave some nutrients behind. And that actually increases the precipitation potential for the next batch because now that liquid is even more enriched in nutrients. That's a very good thing for us, in terms of phosphorus recovery efficiencies. The one thing that this figure doesn't show you is that our acid and base demands do go up a little bit, but they don't go up so much. I think it's like 25% or 30%. And so that's actually quite reasonable, especially because in stage 2 and 3, you can see we're getting over 90% recovery here. And so the fact that we can recycle that process effluent is really key because we don't want to turn a solid waste issue into a liquid waste issue. This allows us to really minimize the volume of that liquid waste at the end of kind of a lifetime. So again, just to recap, we can, efficiently and sustainably extract our phosphorus, recover it as struvite, and then recycle that process effluent back around for at least 10 stages. Now, I think I'm probably running out of time. This is my last slide here.
Okay.
I just wanted to quickly revisit. I told you in the beginning that another part of our lab focuses on contaminants of emerging concern, like antibiotics and hormones. And probably some of you have seen, animal products in the grocery store, say antibiotic-free or hormone-free, but not all of them do. So we wanted to think about this scenario that, hey, if there are some antibiotics in the poultry litter or some hormones like estradiol in the poultry litter, when this poultry litter goes through pairs, what happens to an antibiotic like enrofloxacin or a hormone like estradiol? I wasn't sure, to be honest with you. I was a little bit worried that maybe they get concentrated in the recovered struvite, but I hope you can see here that they basically all remain in the low nutrient solids. So this is like the solids after we extract the nutrients, do the solid liquid separation. These are the solids that remain. So we're not treating the antibiotics, we're not degrading them or, removing them or anything like that. But at least we're not changing the situation. I would be a little bit worried if we saw that they were concentrating, in the struvite, because then say, hey, we're selling this as a, fertilizer product, but if it has a really high concentration of antibiotics in it or a really high concentration of hormones in it, maybe that causes some unintended consequences, that go above and beyond the base case. But in this case, that wasn't the case. So conclusions, I think I probably told you plenty about the pairs process now, and you saw the video. I'll just maybe mention here really quick that our real goal is to develop what we call circular nutrient economies. And so if we can take waste, recover the nutrients, turn them into fertilizer, use that fertilizer to grow food, use that food to grow other food, get the waste, recirculate the nutrients around and around and around. That means we need to pull in less like new phosphorus from Morocco. It means we can be more sustainable overall and reduce water pollution, which was our original driver. So I'll thank our funding sources. Well, thank you for your attention. You should be able to follow these QR codes if you want to see our pairs paper or some of our other recent papers on nutrient recovery. And if we have time, I'd be very happy to stick around for questions. Thank you.
Thank you very much. So this is a really good example of chemistry, like essential and central to producing jobs, potentially producing, helping the economy and helping the environment. This is really a great project.
Yeah, thank you. One thing I'll just say there real quick, you kind of jogged my memory. One of the maybe classic conflicts is environment and agriculture. They're always butting heads. But one thing that we thought when we went into this is, hey, we don't want to blame farmers. They're doing their job. They're producing, food for the country. We don't want to go in and blame them, point the finger at them and say, hey, you're causing all this pollution. We wanted to go in and say, hey, we got an opportunity for you to turn your waste into profit. And that really changes the dynamic of like how we can work together to find the best solution. Exactly. I think that's really important, that we don't finger point, but we work together to find solutions.
That is so cool. Chemistry is great. So to begin the question, I'm wondering, so I think I saw that the acid that you use is HCl, hydrochloric acid, and it adds some cost and stuff. I'm just wondering if maybe trying some organic acids, because you could have sources from, natural sources of organic acids, fruits, could add another dimension, if that's something that you guys have considered.
Excellent question. And one of the reasons why I like it is we have considered it. So I have a good answer for you. Okay. I kind of had a maybe very similar perspective. I said, okay, we need to try this. And so I don't remember, everything that we tested, but, one of them for sure was citric acid. With citric acid, we have 3 protons per mole. So we have a lot of potential to try to bring the pH down, quickly. One of the issues with the organic acids, though, is that they all have acid dissociation constants or pKa values kind of in our pH operational range. So we're kind of like between pH 4 and 9, let's say. We bring the pH down to 4 and then up to 9. And so when we use the organic acids, what we found is that they worked very well for the extraction side, but then they actually increased the base demand quite a lot because now we had to move, through those acid dissociation reactions first. So it increased the base demands dramatically compared to a strong acid.
Yeah. Okay. Okay.
Yeah,
So it solved one part of the problem, but then created another.
Exactly. And one of the things for us again with this one is trying to make sure we can be as economically feasible as possible. We didn't want something that was very complicated, would require a lot of costly chemicals. And actually the base is like the chemical that's most expensive. So the acids are much cheaper for us.
Okay. So, Gabrielle, do you have any comments or questions, and other students as well?
Well, I was going to ask, you kind of mentioned it too, how you did like engineering and stuff, and somehow you ended up doing like chemistry. Like, where was the transition? How did that happen?
Oh, yes, this is great. So I'll be 100% honest with you. Chem 101 was my worst grade of college. I did not like chemistry when I started college. I liked physics, I liked math. These things made sense to me. Chemistry felt like magic. And yeah, I actually started in a civil engineering program. but I wasn't like so motivated. I didn't know exactly what I wanted to do. It wasn't until after or towards the end of my second year of college, I saw a talk by a professor at my school, Lehigh University. His name is Arup Sengupta, and he gave a talk on some of his environmental engineering research, removing arsenic from groundwater in India, working in rural villages, poor villages, and removing arsenic, which is a very toxic chemical from their groundwater sources, for people that had no other option. And I said, wow, this is like amazing. This man is using his education, to save people's lives, like very, very directly.
Mm-hmm.
I thought that's what I want to do. So I went up to him afterwards and I talked to him. I said, hey, can I change my major to environmental engineering? He was like, yes. I was like, can I start working in your lab? And he gave me the chance. And I realized, okay, chemistry is very important for environmental engineering. So if this is what I want to do, I got to figure it out. And now all I think about is chemistry. All I teach is chemistry. Our lab is all chemistry. And so for me, it was saying, okay, what's the impact I want to have on the world? And what tools do I need to do that? And that's when the switch happens. So
Yes, that is a really
That's
cool.
awesome.
I know. I know, and I think a few of us could probably identify with not liking chemistry at first, and then, yeah. So other questions? Other questions from anyone? This was a really cool, I mean, I'm like, this is a really cool seminar.
oh, thank you. Thank
Because
you.
yeah, because it really shows the power of chemistry, and you're doing just basically acid-base chemistry, fundamental
Mm-hmm.
stuff. That's not really over too many people's heads,
Mm-hmm.
And having this sort of impact that would only grow better with time.
Exactly.
Yeah.
Sometimes we focus on the complex just for the sake of complexity, but a lot of times, the best solutions and the most feasible solutions, are ones that are more simple and, just require, maybe a little bit of, thought and playing around with how all the components come together.
Mm-hmm.
While people are thinking of other questions, I'll mention for the students as well. I meant to put this on this slide. But we do have an REU program in our department, research experiences for undergraduates. It's called Be More. It's kind of focused on the interface between biochemical and environmental engineering. You don't have to be an engineer to apply. So I just put the link in the chat.
Okay.
And if anyone wants to check it out, please feel free. Our deadline is coming up next month, March 10.
Okay, so we have good enough time to get that in. Yeah, we've been encouraging our students to, go off and do summer research because it really helps them understand chemistry and whatever topic really in a more in-depth and practical way. This is very inspirational. Thank you so very much. Doesn't look like we have more questions, but we'll be checking in with you.
All right, very good. Well, thanks again for the invitation.
Going. Yes, thank you so much.
All right, you're welcome. Y'all take care.
All right, take care. Bye-bye.